Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the next talk will be by Takun on randomized decision forests and its novel applications.
Okay, nice meeting you. I'm TK from Imperial College, London. So I'm very glad to be here. So thanks a lot for inviting, and also to all for your coming. So talk title today is a little quite big, I admit that, machine learning for visual recognition. But in there, I'm going to highlight a particular technique, which is called randomized decision forest. And I know here are many experts of it. So just let me kind of explain some three of our own novel applications of it. Well, actually, this is the material that I talked to my students at Imperial, so it contains some basic information, but I'm going to go quite quickly. So we begin with the data vector X, image or features convert into column vector, and we do some unsupervised learning for density estimation. So manifold learning is also one of them. And then if we have a labels of variable, then we learn some mapping function from input to output. So it's unsupervised supervised learning now. So we do some classification, some techniques very often used in the field include boosting, maximum margin classifier. Also when the target vector is continuous, then obviously we do regression, polynomial curve fit. So sorry about excellent handwriting. And also Gaussian process is also one of those popular techniques used. Okay, key thing in the area is generalization to unseen data. Given a training data, estimating the density function P or the mapping function F is relatively easy. But then how we go from left to right when kind of new test data points are given, those learned function P or F should be working well for new data as well. So this is typical saying though, in computer vision, the data are in very high dimensional space. So, and also due to their large intraclass variations, practical assumption is that we never have kind of complete training data. Always test data points are quite different from training data. So how to go from to the left to the right is much more challenging in computer vision than I think were relatively some other fields. Okay, there are many techniques about how to ensure good generalization. So polynomial curve fit, where in addition to error term, it also has a regularization term, so it avoids overfitting. And also obviously a super vector machine that has a notion of maximizing margin, and that is given by that objective function. And also Gaussian process that places some Gaussian prior distribution on the weight vector W. So actually, quite interestingly, there is a kind analogy among the different methods, different state of the art, but always doing kind of good generalization, particularly on the weight vector W. So obviously there are some other types of methods, like boosting, that also is quite good at generalization to unseen data, but in a quite different way from the previous. So it combines weak classifiers linearly. So linear summation of weak classifier outputs are the output of strong classifier. So by having that weak classifiers relatively naive, reasonably naive, and the linear summation doesn't go that much overfitted. So obviously there is no theoretical guarantee for good generalization, but practically has been pretty well known and working well for the challenging visual recognition problems. The other kind that I particularly would like to emphasize in this talk is random forest. So that's my illustration of random forest. So if each weak classifier is seen as a decision stump, then actually the random forest has also analogy, quite similarity with the boostings. So that's what I'm going to explain a bit further in the following slides. Obviously, this slide compares some two popular techniques in terms of optimality. So when you do visual recognition, obviously recognition accuracy is kind of key criterion. But then actually I want to a bit focus on the other criterion, which is computational efficiency. So here we compare boosting and support vector machine, where this is quite basic. So basically, the boosting seems much faster than nonlinear SVM. But when SVM adopts linear kernel, then actually that computation, this kernel computation can come out of the summation. So actually, that computation demanded by linear SVM is also quite efficient, quite low. So whether boosting is more efficient than linear SVM depends on how many number of weak classifiers to use or what's the dimensionality of data vector. So D. Okay, then why, we are particularly kind of taking care of the computational efficiency. So there are many such kind of computational demanding problem. One is object detection. So from a given image, we have to scan every possible scales, in a typical approach, and have to scan every pixels to detect pedestrians. So you have to classify. A typical image is comprising of millions of sub-windows. We have to classify. So we have to kind of tell whether each sub-window contains an object of interest or not in a very fast manner, so to complete this task in a reasonable time. Okay, so that boosting classifier of Viola and Jones has been very successful in the field. So our own interpretation of it is very shallow network. So we see that each weak classifier now is a decision stump. So we have many of them. When a test data point is given, it passes on to every weak classifier, every decision stump, and then their outputs are linearly aggregated. So that flat structure, very shallow structure, often provides a very smooth decision boundary, which is good for generalization, so good accuracy. However, that flat structure, as it has to use all the weak classifiers, in computational efficiency, it's suboptimal. So people often use cascade of it. In that cascade, each node is a strong boosting classifier, but it does kind of cost-define search concept. But actually, designing that cascade involves quite parameters to set, manually or automatically. So this is alternative. Well, this is random forest, a slide of Jamie Sharon. I store it. So it has hierarchical structure. It's quite similar to that boosting cascade. So that owing to the hierarchical structure, it's quite fast in both training and in testing. Also, another advantage is that it can do multi-classes, and also where that randomization in the feature split and also randomization in the data aggregation, which is bagging, it's quite kind of practically good at generalization, smooth decision boundaries, and recognition accuracy. So here's a quick comparison between the very traditional random forest, traditional decision tree in the left-hand side. And in the right-hand side, I'm showing the kind of conceptual notion of random forest. The decision tree is very kind of notoriously bad. As it keeps splitting the tree, nodes, it can always kind of dichotomize all the training data points. So when to stop, it is kind of a big question. So many studies have been done, but unfortunately there is no such kind of principal rule. So it often ends up with this overfitted decision boundary. But instead, random forest, even with fully grown trees, by having those trees, each tree is slightly different from others, and by combining them, it does some kind of smoothing out effect, perturbation effect, right? Just kind of conceptual comparison. So it does kind of pretty provide a good generalization. In our one of the latest work published in IGCB, we formulated this conversion properly from the boosting classifier in the left-hand side to the decision tree in the right-hand side. So we take a boosting classifier, learned in a standard way as an input, and then we produce some classifier in this tree structure as output. But in this conversion, one key thing is that we preserve the decision boundaries of boosting classifier, because it's pretty kind of reasonably smooth and good for generalization accuracy. So we converted from boosting to decision tree by preserving the decision boundaries of boosting classifier. But as a result, as it's in a hierarchical structure, owing to having many short passes, it could accelerate the variation speed. So in here, just given the decision regions of boosting classifier, each subregion of it is reached by one pass of that resulting algorithm. So obviously, it has some short passage and also long passage depending on difficulty of samples to classify. Okay, now let me explain some our own applications of random forest. One is real-time action categorization. So in here, actually, we use the random forest as a code book of space and time. And we could do kind of this action categorization almost in real time. Okay, some major contributions lies in where so we do that we learned the code book of spatial temporal space using random forest. I shall briefly explain it. And also we capture some structural information among many interest points in addition to the semantic information. Also some other contributions include some extension of fast corner detector into space and time. And we could do continuous action recognition. So instead of k-means clustering, typical approach for codable, we use random forest in space and time. Also we capture, so it's very efficient and also robust, and also we capture the structure information using the learned random forest codebook. And also it could do some hierarchical matching to relieve some quantization effects. So here's a quick overview. We detect interest points, and then we extract some spatiotemporal cuboids around each, and then we quantize them using random forest codebook, and then we capture some structure information by the technique powered by random forest codebook, and then finally perform some, again, tree structure classification. So all could be done in very fast manner. Okay, so here's about that semantic taxon forest of space and time, where each cuboid is passed down the tree, and each split node, we just simply look at 2 pixels in space and time randomly, and then we compare them. Depending on the comparison, we just pass it to the left or right. But it's very similar to semantic taxon forest, Jamie, but it's extension to space and time, and for the first time. Then this is about how we capture the structure information. Given a pair of cuboids, we pass them down the trees, and then depending on the leaf nodes they're arriving, we increase the corresponding histogram bin. And also we have some heuristically defined the kind of regulation rules. It's like kind of one cuboid is before or after the other, or how adjacent they are, kind of things. So it has this kind of 3D histogram. As you have many trees in the random forest, so we have many of those histograms. And finally, we match kind of hierarchically. So we perform pyramid match kernel, but in a very efficient manner, because we have random forest. It's inherently in hierarchical structure already. So actually, we could perform this one in a very efficient manner. Okay, we did 2 benchmark data sets, KTH and UT interaction data set. And so there are a lot of studies in the area. And in terms of accuracy, we are quite happy to have at state-of-the-art accuracy. It's not much worse, quite competing. But in terms of speed, for KTH data set, we've got about 20 frames per second. And for UT interaction, we got 10 frames per second. Okay, a bit further demonstration of the work. So in here, we are processing frames about 10 to 20 frames per second. Also recognizing, classifying into one of 6 action categories. That yellow bar indicates the confidence, amount of confidence on the current recognition. So it's quite robust about that camera viewpoint changes, also some scale variations, which will be shown later. Right. Okay, now this is second example. So we do phenotype object recognition using 3D shape priors. So phenotype here means whether that object is slim or fat or tall or short or muscular or something. So given a query silhouette, can it tell the which object, which person this silhouette should belong to from the given galleries? Which is second man, the left-hand side. So we attempt this one under deformations, so it is articulation of a human body, and also we do the same thing under 3D camera viewpoint changes as well at the same time. It's highly challenging based on single gallery silhouette, single query silhouette. So we do use 3D shape priors. So these works have been published in ECCV and ICCV in recent years. Okay, here we show how we learn the 3D shape priors. So actually we decompose problem into two. One is shape and the other is pose variation. So we learn shape generator from the 3D graphical model of human bodies or in the canonical pose. Actually we used a generative technique called Gaussian process latent variable model. So from the given that PCA coefficient of vertex positions, given that some latent value, it could generate the shape. And we apply the same technique to pose variation. So that is learned from this 3D graphical model of canonical shape, but with the pose variations. So we use the same technique to capture pose variations. Okay, from learned two GPL VMs. So where in the left-hand side and right-hand side we showed some cross-section of latent spaces of GPL VM for shape and pose, respectively. So by taking one value in the left and the other value in the right, we could generate some arbitrary shape and pose. So we started with the zero shape, and then we learned the pose variation. We also learned shape variation, and then using some pose transfer technique proposed in the graphics area, we could generate arbitrary shape and pose as well. So this model is serving as our 3D shape prior. So now I'm explaining how we perform phenotype recognition using the learned 3D shape prior. It's basically, by this graphical model, we use random forest here to hypothesize the latent values from given single query silhouette. So we have three different random forests. So one is for pose and one is for shape, and also the third one is for camera pose. So once we have some estimated value of the latent variables for each of variation, then we could synthesize arbitrary shape and pose, and then we project it into some certain image plane, having silhouette of it, and comparing the silhouette with the query silhouette, we could perform phenotype recognition. Here's an example of a tree for shape and pose classification. So we have many of them, slightly different. We also proposed some novel way to compensate errors using this kind of metrics. So we have collected our own data set, and we have compared some relevant methods, but actually most are 2D. And one is using the same 3D shape priors, but using different technique rather than random forest. We have compared them with our own variations within the framework. And those red bars, reddish bars are our own solution, and those blues or greens are others' methods. So using that 3D shape prior could improve the recognition accuracy quite significantly. So in the left-hand side, it's about human data of jumping jack, and in the middle, it's for walking, and right-hand side, it's for shark of some deformation sequences. So this is some intermediate shape reconstruction result. Because after estimating, hypothesizing the latent values, we could generate this arbitrary shape from given single silhouettes. So input and shape estimation and pose estimation, and the same at the different camera viewpoint. So same for human images. So input image and estimated shape and pose, and just at a different camera viewpoint. And by the pose transfer, we could convert them into some canonical pose. So in here, actually, there's quite varying phenotypes estimated. Okay, this is the latest, the final that I wanted to explain. Well, it's ongoing work under submission, so let me go very quickly about it. So in here, we do video-based object recognition in real time. displaying that object name with a confidence value. Okay, in this formulation, we have all kind of models and query as videos. So we perform video to video matching. Okay. Where this is kind of some conventional image-based recognition framework. When the video is a variable, actually, there is relatively much rare work on video-based object recognition. Mostly, they're about image-based recognition. Even if video is a variable as input, they typically kind of take video as a set of images. So they perform frame-based recognition, frame by frame, and then they accumulate the frame recognition scores in a rather simple manner. So this could be one example of it. From a given image, we detect interest points, and each interest point is passed down the random forest codebook, and then each image is now a histogram vector. So using some classifier, they recognize each frame and then just sum up their score values. But our argument is that actually we could do better. There is a bit more information, like kind of temporal continuity, some set properties we could make use of for better object recognition in video when video is given. Where I'm guessing that one reason why the people haven't given their attention to the video-based object recognition is that in the scenario that we consider, the camera motion is random. So we think of the scenario where the user is moving their camera around an object of interest. So this motion is quite different from that motion in the study like action recognition or gesture recognition, where the motion is key discriminative information. But in here, due to the randomness, actually we have to explore some different properties for video recognition. So just briefly, key concept is set of sets. From given a video, we have many images, right? So a set of images, and then each image we detect interest points over. So we have a set of interest points. So by going down, we have a set of set concept. Also, if you look at one image patch and track them through the time, then we have a trajectory, and then we can collect set of image patches along the track as well. So after that tracks, we have many of them, so it forms another set of set concepts. So actually, we've been studying about how to represent this set of set concept, how to match one to another for video-based object recognition. Where just very brief concept is that we rely on popular representations of sets. So one is bag of words. That's indeed a very popular way of representing set of interest points. So we use it. Also, another technique is manifold. The manifold is particularly good for representing set of data temporally smoothly changing. So we use them in a kind of a bit recursive fashion for set of data spatially distributed and set of data temporally smoothly changing. So obviously we have some alternative as well. Where in here actually we also bag manifolds, but the manifold is not single vector, but it's described by a set of based vectors. So actually we needed some new technique on how to bag the manifolds. That's a bit of details in the work. So here's our new data set. And we compare some simple frame-based recognition or simple accumulation of it on different object categories, object instances, and we are performing significantly better. Also on different kinds of variations. The training data is just a single turntable sequence at the fixed height and with the camera at the fixed height at different day and different time. So it could work in real time, nearly real time, and also it's quite robust about 3D, 2D rotations, also some foreground clutters and background clutters, some illumination changes as well. So we are testing completely different day. It works pretty well. Okay, so apart from that, what I presented, Some ongoing funded projects are including real-time multi-class object detection. So we consider some different object classes that have different aspect ratios, width and height. And in there, can you detect all of them in kind of close real time? That's kind of one of our questions. And also we do continuous learning, 24 hours and 7 days learning, rather than just learning single time in offline fashion, deploying into new environments. It's not going to work. So that we're interested in kind of exploiting all the variable resources in the internet as much as possible, keep improving the performance. That's by the joint work with the NUS. Also, we do some deformable object recognition. And finally, we are very interested in gesture interface by 3D tracking of human hands. Okay, that's most of it. And this is a snapshot of our group at Imperial College. So, well, yeah, any questions and comments?
Time for a few questions. Yep.
For the pose estimation things, I was wondering how scalable it is. So you were just showing a few poses. If you want to do something like really reconstructing the posture from the 2D silhouettes, how applicable is your method?
That's true. At the moment, actually, our algorithm is specific to certain pose. So we need some motion capture data or something like, and then we collect a lot of 3D graphical model with that pose variation, and then we learn generative model like by GPLVMs. So,
so you can learn a lot of models. So I was wondering whether this framework it's doable for really recognition of arbitrary poses.
Well, yes and no. I mean, yes, obviously, we trained the same algorithm, GPLVM, on a lot more pose variations and etc. is possible. But then the challenge would be about how to control that kind of dimensionable latent spaces. And I think just naively applying the current technique to all kinds of pose variation is not going to work. A bit more cleverness would be needed, I guess.
Okay, so if we don't have any more questions, let's thank Taekyun again.